So, first of all, I would like to thank the Portuguese Association of Data Science for the invitation. It's a pleasure to be here. A lot of people interested in this topic. It's very heartwarming to see so many young people interested in developing a career in this area. I would like to start by taking a very quick poll. I'm going to show you 3 different photographs, and I just wanted you to raise your hands if you know the guy in the photo. So the first one is this. Anybody knows him? Okay, we have some. The other one is this one. Okay. And the last one is this one. Okay. So these 2 first guys, this one is Jeffrey Hinton, which is kind of, it's not the grandfather, but it's one of the many fathers of neural networks, and most notably the father of deep learning. Okay? And this second guy is Yang Wutun, which is also one of the fathers of neural networks. This guy came up with the convolutional network in '89 or something like that. And now he's head of artificial intelligence in Facebook. And so these 2 guys are kind of like rock stars in the field. Not so popular as rock stars, but probably making as much money as rock stars. They do a lot of money. This third lady is called Fei Lin. And I would like to speak a little bit more about her in 1 or 2 minutes, okay? So, because I think that she has been instrumental for all the changes that we've been seeing in these last few years in the area of artificial intelligence. So, my point for today is this one. It's kind of counterintuitive because we live in the deluge of data, right? We have data everywhere. My point is that data sets, not really algorithms, are the key limiting factor for the development of better data science or for better artificial intelligence. And this is probably one of the topics that we tend to forget when we talk about artificial intelligence and data science. So before I go into my argument, I just wanted to take a step back and give a brief overview of what I consider to be supervised learning, because supervised learning has been the most successful type of learning that we have, and I would say that probably 95% of the whole money that is made in data science is based on supervised learning. And so the idea of supervised learning is something like this. We have a set of inputs, and we want to train a model to predict a certain output. Okay, and in here between these inputs and the output, we will have some algorithm or model that is able to map the inputs into the output. So for instance, if we want to design a classifier that is able to distinguish between oranges and apples, what we need to do is to find or decide what are the characteristics of these fruits that we want to use to make the distinction, take the measurements, and then for each case use the appropriate label. In other words, if it's an orange or if it's an apple. And if we do this, so in this case in my model I have the weight of the fruit and the color. I get something like this. And the role of the model is basically to design this line that we have here, that will allow us in future cases, based only on weight and color, to attribute the label to the input that we have. And so this is basically the idea of supervised learning. This is the general, let's say, schema for developing a classifier. We start with a labeled data set, and so don't forget, the labeled data set is where we have inputs and outputs accordingly, okay? And this is what we use to develop our knowledge. And the algorithm, basically, the algorithm doesn't create knowledge. The algorithm extracts knowledge. And this is the key issue here. The algorithms are used to extract. They don't create any type of knowledge. Okay? And so, using some appropriate algorithm, we will be able to extract some knowledge, and then we'll have a classifier. For these new examples, in which we only have input variables, we'll be able to give it an appropriate label or an output value. Okay? Okay, so this is obviously conceptually very simple. what are the problems? Well, there are many different problems that can happen in this process, but I wanted to focus on the data problems that we may face, okay? Sorry. And so the first problem is this. Do we have the relevant features or attributes or variables that will allow us to make good predictions? As I said before, the algorithm will only extract the knowledge. It doesn't create knowledge, okay? And so if instead of weight and color, I'll use the ripeness of the fruit and the number of seeds, I'll get something like this, which is hopeless. No algorithm will ever do a good classification between oranges and apples using these two features. So the first problem is to get the appropriate features, the knowledge that we afterwards will extract. The second one is, and this is a very significant problem, is do we have enough data, labeled data, to build a model? So sometimes we think we have a lot of data, but we don't have enough data in the appropriate conditions to develop a model, okay? The second one is that we have to know to which each example corresponds. So each example for each example I have to know if it's an orange or an apple, right? This seems kind of stupid to say, but for instance, if I'm an insurance company and I know that I have fraudulent claims, but I'm not able to specifically point out which are the fraudulent claims, I won't be able to develop a predictive model. Does that make sense? Okay. So this is sometimes very important. I know that I have fraudulent claims, but I'm not able to identify which are the fraudulent claims. Okay. This third one is also important because sometimes we want to develop predictive models for labels that we really don't understand. And in this case, this would be the case of churn. For instance, most companies want to develop a churn model. But when we start discussing what the churner looks like, nobody gets into agreement, okay? Is it somebody that doesn't buy in our store for the last 3 months, or for the last 6 months, or the last year, or whatever? So we have to have a very clear and well-defined concept of what we are trying to achieve with our predictive model. Finally, one other problem is this problem, which is also in the research known as imbalanced learning, when we have a lot of examples of one class and a very small number of examples of the other class. And so, for instance, if we have something like this, in which I have 99% of the examples are from the negative class and only 1% of the examples are from the positive class, and if I use the most stupid classifier that I can use, which is classify everything as a negative, I will get an accuracy of 99%. Okay? Although the classifier is useless because it will never identify a positive example. Okay? So this is yet another example of the problems that we face when trying to develop supervised learning models. Okay, so back to Fei Li. Some of the people here knew who she was. Fei Li is a professor of computer science in the University of Illinois. And she came up with this stupid idea of, instead of developing algorithms for her research, to develop a data set. You see, you have to understand that for academics, what is important is to develop algorithms. It doesn't make sense for academia to develop data sets. That's stupid, you see. And many times, many different people told her that what she was doing was stupid. It was not really science. But Fei Li, being an Asian and a go-getter, continued to develop her efforts. And eventually, in 2009, she made available a data set which is called ImageNet. Do you know what ImageNet is? Okay, so ImageNet is the data set that it's, sorry. Now I have the problem. Oh, sorry. Okay, ImageNet is the data set that underlies this large-scale visual recognition challenge, which is something that happening between 2010 and 2017. Okay, and what Feifeli did was to come up with this data set, which at the time had like 3 million images, all of them noted, and so we had the label for each one of the images, and she promoted this competition. And what I wanted to highlight here were two things. The first one is that in 7 years, and remember that the computing vision field has many decades of work before this, okay? But in between 2010 and 2017, we went from an accuracy of 71.8% to an accuracy of 97.3%, okay? Just in 7 years. And in fact, this type of accuracy is higher than what we humans are able to do when labeling images. Okay. The second thing that I wanted to point out is that today we all talk about deep learning, and this idea of deep learning being a very powerful tool to make supervised learning came in 2012 because of this competition. And here, because of these results more specifically. In 2012, Jeffrey Hinton, the first guy in the picture, entered the challenge and was able, with the deep learning network, to have an accuracy which was 10.8 percentage points higher than the second team. Okay? And this was the starting point for all this craze around deep learning and artificial intelligence. As you can see, the evolution was very quick, and most of the teams by 2013 were using deep learning. And nowadays, all of them use deep learning, and as you can see, the results are fairly close together for all the teams entering the context. So I think that this graphic gives us a very significant, oh, I have 2 minutes, so I have to still. This graphic gives us a very significant message, which is the appropriate data set may change everything. And this is what happened here, okay? Now, although deep learning might be a very interesting technology with a lot of promise and the ability to deliver very, very significant and important results, you have to keep in mind that these deep learning neural networks are applied mainly on unstructured data, like images, text, sound, video. Because if you go back to the Kaggle competition and you look at the competitions with structured data, it's not deep learning that's doing the best possible results. Okay, but with deep learning, we got this idea that contrary to the other algorithms, which have some type of saturation, the more information you give them, they don't improve as much. In the case of deep learning, it seems that the more data you give to the model, the better it gets. Okay, and we still didn't find any threshold or limit for this improvement. Okay, so this is yet to another example of why I think data is a fundamental aspect of our activity. Here we have some significant breakthroughs in artificial intelligence. Here we have the data sets that were used to develop these breakthroughs, and here the algorithms. And if you analyze this table, you can see the algorithms that we are using for these big breakthroughs are much older than the data set. So the limiting factor for these breakthroughs were not the technology, the algorithms, which on average were available 18 years before, but the data sets that we are using, which on average were available only 3 years before. Okay? And so this ability to create good quality data sets is one of the most important aspects for the progress of data science. Okay, yeah, just one or two more slides, okay? So my point is the bigger data leads to better decisions, and we have this saying that simple models with lots of data will usually perform better than complex models with small amounts of data. The example of Watson is yet another one. Watson is an amazing machine from IBM, but it has had all sorts of problems applying its, let's say, its technology to healthcare. Because in healthcare we don't have a lot of data, and most of the projects in which Watson is being used are being now stopped or closed. How much time do I have? Should I stop now? None? Don't I have any type of tolerance? Or 15 seconds. Okay, so let me just show you what data scientists think. So this is a survey that was done in 2017 with data scientists, I think 200 of them, and they came up with this, or they answered a certain number of questions like what's the activity that takes the most time in your work, which obviously is collecting and labeling and cleaning data sets. What's the biggest bottleneck of in running successful IE machine learning projects? Again, it's improving the quality of or getting good data sets. And finally, this one is the most interesting one, which was, the question was, would you rather accidentally delete all your training data with no backup, accidentally delete all your machine learning code with no backup, or break a leg? And amazingly, there's more people willing to break a leg.
I'm about to
break a leg than to delete their own data set, okay? So I don't have time for anything else. I'd like again to thank you everybody.